Hi everyone, welcome to the second video on the video series I have for the package tsBNgen. Today I would like to walk you through this file that I have in my GitHub, time series generation examples. And this is a Jupyter notebook file that is already there. You can download it, clone it, and then look at it at the same time with me. Or in the next video, I'm going to walk you through that with using Python. So how to install this package and how you can actually use this package to generate any, I would like to say that time series correspond to any Dynamizer network structure. All right, let's start. So here a little bit about the package. The package is called tsBNgen. The idea for the name is a time series Bayesian network generation. So it's a Python library to generate time series data according to arbitrary Dynamizer network structure. What is dynamic Bayesian network? In the last video, we talked about the static Bayesian network. So in a static Bayesian network, you have something like this. So let's say this is a network you have. This is a network that we discussed in the last video. Dynamic Bayesian network is that you copy this network over time. So it has a temporal connection. So if I take this one, and so if I copy this and put this one here, and then so to put this one here for 3 time point, right? So for example, you can get this. Let me just make it simpler a little bit. Let me erase D. Let me make sure I erase D. And then what's going to happen here? This is B1, this is A1 for time 1. This is B2, this is A2, this is C2, this is B3, this is C3, and this is A3. So dynamic Bayesian network, for example, can be like this. They know that the previous time, for example, can be connected to know that the current time, and so on to the future as well. So this is an example of a dynamic Bayesian network with a loopback 1. We talked about this, the loopback 1. All right, so this is a dynamic Bayesian network, so example of that. So this package allows you to do much more than what you see here. Now, this tsBNgen is released under a MIT license. This means that if you cite the paper that I have in the GitHub, you can pretty much free to do anything with the package you like. All right, so the instruction is that either you can clone this repository that I have, or install it through pip install tsBNgen as part of the Python library now. After you install that, then you're going to go ahead and issue these 2 commands. So this means that you import everything you want. You don't have to import everything, but this assures that everything we have in the package is going to be working. All right. So now there are 2 important functions. This is where people are confused here, these 2. So for the most part, for the dynamic Bayesian network you see in the literature, for 95% of the time, this is good enough. BN data gen, BN underscore data gen. What it does is that this is used when the custom time is not specified. All right, you see this for this dynamic Bayesian network that I have in this figure. So this is an example that you see a lot in the literature, this type of example. Custom time is not specified, means that a network at time t is connected to a network at time t minus 1 or at time t plus 4. This is what it means. The loopback is 1. Sometimes you want to say that, hey, I want this node A1. I want this node to be connected to, I don't know, I want this to be connected to B2 or B3. This is possibility, right? I want to have a very crazy structure. Then A2, for example, be connected to B4, something like that. I want to have very crazy structure, right? So anything you like pretty much, arbitrary, dynamic Bayesian network structure. If you want something crazy, then that function BN data gen will not allow you to do that. Then you have to use this function, BN sample data gen loopback. So if you have a loopback of 1 for all the variables, means that they are connected to the previous node and the future one, right? Then this BN data gen is good. Otherwise, you have to use the other one. All right. So when do we use this function? This function BN sample gen loopback is anytime your loopback is not 1. Think of it like that. Any structure you have, if the loopback is not 1, and the loopback is specified by the loopbacks 2, which I'm going to talk about once we get there, you should use this function. All right, very good. So now let's see what are the variables in the package. T is the length of time series. So it's the length of the dynamic Bayesian network, is the temporal length of that. So for example, T for this network that I have, T is equal to 3, right? So T is the temporal length. N is the number of samples, so number of observations. So for example, let's say you have an algorithm, you want to try that, you want to generate 10,000, 100,000 data, and each one you want it to be 100 points in time, right? So the N is going to be 100,000, 100 patients, 100, I don't know, 100,000 patients, 100,000 students, whichever quantity you're dealing with, right? So if you want to have a good understanding of this, consider this data that I have. This is going to be, so let's say S1, S2, all the way to Sn. This is the number of samples, and this is across time. You have X1, X2, all the way to Xt, right? So this is first sample, this is second, and all the way to n sample. All right, very good. Now the number of level. So this is a list. So these two, the first two are integer, let's say that 10, 100, and the number of level is a list, the number of possible level for the discrete nodes. So we talked about the last video. If you haven't checked it out, I will put a link in the description. So go and check that video first. So the number of level is for only defined for discrete nodes. For continuous nodes, we use a Gaussian Bayesian network. For discrete nodes, we use multinomial. So now, in a sense, if you consider, I would write it down here, I would consider that if the A is binary, we can represent A like this. A can take 0 and 1. So the number of level for A is 2 if A is binary, right? Then P of A equal to 0 can be 0.6 or 0.4. I described this one in the last video, all right? So this is only for discrete nodes. Great. Then math. This math is the most important, one of the most important variables here, which is short for a matrix and short for adjacency matrix. So what this math represents is uniquely tell you what is the structure of the Bayesian network, right? So let's say if you have what I have here, this graph here, right? So the math adjacency matrix is corresponding to each time point, right? So for example, it corresponds here for a static Bayesian network. So what's going to be that? It's going to be 3 variable ABC, right? And then so A and A. So this is for directed graph. I talked about the last video. So A and A are not connected 0, but A is a parent of B 1. A is a parent of B1 and A is a parent of C1. B is not connected to, is not parent of anything, and C is not parent of anything. So that's, you can see that B and C are the leaf nodes actually. So they don't have any parent. Now you might want to say that, okay, hey, they are connected to another time point. This is for a static Bayesian network. This tells us what type of graph you're actually thinking, what type of graph you're envisioning, right? So that's a math, adjacency matrix, all right? So then we go to the node type. It's a list. Math is a data frame, right? You see this should be a matrix data frame, right? NumPy array. But it's as a, we have it as like a math as a data frame. Now, node type is a type of each variable. We need to specify that, otherwise we don't know what type of distribution or we should use for them. Is it continuous or discrete? So the node type can take the value of C for continuous and D for discrete. All right. And then we have a CPD, conditional probability distribution. So that's a dictionary. Why is that dictionary? Because so what the way it works is that, and usually is that for this CPD, for a discrete variables, we have a table. For continuous, we have a Gaussian. Now, so we don't really use A and B and C, the names, because the names are arbitrary. You can change that. We use the numbers here. So, and it's based on topological ordering. So this, the A is coming first. You have A 0, then B and C are the same. So you can say B is 1 and C is 2, right? So you say that 0 is a key of the dictionary, and then based on this, what is the distribution of that? And then for the 1, what you say is that, you know what, I have to uniquely specify this variable, right? And therefore, and since we showed that in the last video that the distribution of a variable in Bayesian network is depending on the parent's distribution, right? It depends on a parent distribution. Therefore, here what you have here, instead of writing, so this is 0 only, and then instead of writing only 1, you would write 0, 1 to show that, hey, 0 is a parent of that. Walk you through this example. And for a 2, you will have 0, 1, 2, right? So in this case, you will have 0, 2 actually, because only 0 is a parent of 2. All right. I have example, a lot of examples to show you that. The parent now, this so this CPD is for initial time point. What's the intuition behind this? Is that if you look at this dynamic Bayesian network, or any dynamic Bayesian network per se, the first time point is different from the other time points, right? Why is that? It's because, for example, if you consider this, for example, the parent, let's consider parent. The parent is a dictionary and tell you that the parent of each node in a graph, right? So for example, in the dictionary, the key is 0. What's the parent of 0 here? 0 is a root node. This corresponds to this one. It's nothing. What's the parent of 1? It's going to be node 0 is the least. What's the parent of 2? It's going to be 0. But this is for initial point in time. Now, if you go to the second Bayesian network, the second architecture, let me choose another color here. This one, what's the parent of 0? It's going to be another node 0. The parent of 0 is a node 0 because it's connected to the node the previous step. So you need to say to the network how they're connected together, right? In order to sample it for you, you need to say that to this package, right? Because A1 doesn't have to be connected to A2. This is not just a very limited package that can handle only a basic Bayesian network. So you need to say that. And this parent for initial point in time is different from the CPD and parents are different from CPD and parents for the next time points, at least for even a simple exercise of the Bayesian network. All right. So then we go to CPD2 and parents 2. And this allows you to actually, so up to parent 2, up to CPD2, and parent up to this loopbacks allows you to model any classical Bayesian network, right? So this CPD2 is the CPD, is a conditional probability distribution for a point time 2 onward, right? And this parent 2 is the same thing as parent, but for any other node after time T2, right? So this is going to be T1. This is going to be T1. Okay, so it doesn't like it. So this is going to be T1. This is going to be T2, and this is going to be, let's say, T3. So this parent and CPD is only for T1, and parent 2 and CPD2 is for T2 all the way to T, all the way to TT. All right. And the loopbacks is telling you, describing a temporal interconnection between nodes. It tells you that how they are actually, the nodes are connected. What's the length of that? We will go over the code. The loopbacks is a dictionary. The keys are the nodes, the variables in a graph, and actually the values are the list, which we're gonna actually, I'm gonna show you how this works. Now, so you think that you're done, and you are for most of the Bayesian networks you see in the literature. But then these three will allow you to do anything you like. So up to this point, up to this loopbacks, you can actually issue this function. Up to this point, you can use this BN data gen. But then after that, you want to do something really crazy. You want the it says I use this entry when the BN sample gen is called. Yeah, so you want to actually model anything you like, pretty much. Something not classical DVM, right? You want to have loopback from any node to any other node, any length of a loopback, right? I don't know how this can be useful, but let's say that you want to generate some sort of data correspond to the model that you have, very complex model. The parent tree, the loopback tree, and CPD tree, they are different from the before. So let me just motivate this idea is that, so in this Dynamizer network, you say, okay, you know what? The initial time point is a little different from the second time point and the third time point, but then right after that, everything is the same. But then in this structure of the CPD3 parent tree loopback 2, you might want to say that, okay, let me see whether I can I can do it here. If not, I can do that. No worries. All right, so let me just erase these. All right, so on this one, if you want to use this new thing, is that, okay, so you have this up to this point, up to the point 3. Now you want to say that, okay, you know what? I want to do something crazy for the point time 4. So from this point on, I want to switch, right? And this is the point that you're going to go ahead and perhaps start doing new stuff. Or you know what? Who says that I should do this? I want to go ahead and, who says that the loopback should be 1? I want to go ahead and connect this one to this. Or why even that one to that? I want to connect this one to this, right? I want to do any crazy structure I have. Once I walk you through the code, you will see that actually. I have an example for this, right? So just keep in mind that these three are for more advanced stuff, for what you see mostly in literature. Up to loopbacks is enough. All right, so let's just go over fun stuff now. Walk you through this code here, and then next is that walk you through the code in the next video through the Python. All right, let's take a look at the first architecture here. It says 2 discrete and 1 continuous node. This is actually similar to one of the architecture of HMM. If I'm not mistaken, it's gonna be like input output HMM, I guess. I'm not sure, but that's where the motivation actually was coming from. Let's take a look at that. T is 20. We have 20 points in time. This structure that you see is gonna, not this one, but it's gonna repeat at 20 points in time. N is 2000. We have 2000 objects, 2000 students, 2000 patients, 2000 anything you like, 2000 products, right? N level is 2 and 4. The first discrete node is has 2 levels. The second one has 4 levels. And then math is, now this is important. The adjacency matrix, let's take a look at that. Is we have 3 nodes because we have 3 columns and 3 rows. It's always a matrix. Is a square matrix. I mean, so what we have here is that, let's say we have a node 0 here, and then we have node 1 and we have node 2. So 0 is connected to 1 and 0 is connected to 2, and then 1 is connected to. All right. So that's the structure of it. This is how you say that this is a graph I want to repeat through time. But the static part of that is going to remain the same. So someone might say that, hey, what if I want to change the graph as time passes? Well, this is going to be infinite many possibilities, because there is no way we can actually envision what you want to have in a network, right? So this is going to be the structured graph that's going to repeat, but the temporal connection can change. Now the node type is going to be DDC, discrete, discrete, continuous. So this is going to be discrete, this is going to be discrete, and this is going to be continuous. Okay. Now, so the CPD, the conditional probability distribution, it's going to be for the first node. You see that for the 0 is a dictionary. For the 0, so 0, remember, has 2 levels. For the 0 is going to be binary. Meaning what? Meaning I'm going to write it like this. This is for the node 0. You can call it A. So probability is this node 0. This is a string. Equal to 0 is equal to 0.6, and this is equal to 1 is equal to 0.4. Now for 0, 1 means that I have a node 1, but its parent is 0. To make sure that there is nothing, there is no way that the package can go wrong, right? So for this one, you see, it has 4 levels. I talked about that in the last video. If you have 4 levels and the parent has 2 levels, you have 8 different possibilities, right? So this has also 8 different values in it. And what they mean is that, so let's call this one name to make sure that we are not mixing a lot of things together. Let's see, this is B, this is the A, and this is C. I have it here as well. Okay, this is for different for the node type. All right, so now we say that probability that B equal to 0 given A equal to 0 is equal to 0.4. Probability that B equal to 1 given A equal to 0 is equal to 0.3, and probability B equal to 2 has 4 levels, right? Given A equal to 0 is equal to 0.05, and probability B equal to 3 given A equal to 0 is equal to 0.05. That was the last one, 0.11. All right, so they add up to actually be 1, right? But I think of it, it's A equal to 0 is equal to, it's replaced with sample space. So it's still a probability, so it should add up to be 1. And then the next list, this is the first list. The next list is going to be the probability that B equal to 0, B equal to 1, B equal to 2, B equal to 3, but conditional A equal to 1. So you see, 8 possibilities. All right, so you can specify this one easily. This is for initial point in time. Now 0, 1, 2, this means that the node 2, but the parents are 0 and 1. The parents are 0 and 1. But now this is a Gaussian. This means that for any combination of the parents, you will have 1 distribution. So you have 8 Gaussian distribution for any. So why is it 8? Because you have 2 levels for node A and 4 levels for node B. So 8 different possibilities. So you have 8 mu. So starting from mu 0, 8 mu's and sigmas, and all the way to 7. All right, it can be anything like. The parent for initially, we talk about that. The parent of node 0 is nothing, it's a root node. The parent of node 1 is 0, node 0. And the parent of node 2 is 0 and 1. Okay, so you set up the first initial time. Now, after that, is just copy and paste, right? Because now all you have to do is just find the CPD2. So this line, this two are the same, so you can remove one of them. So parent 2 I repeated twice, but they are both the same value, so it doesn't matter. So you can have CPD2. Why is the CPD2 different? So again, repeat it here. So CPD2 for time T2 and onward. Therefore, this 0, 0, it's going to be what for CPD2? The 0, 0 is going to be the 0 that we had before for CPD. Where is the here? It's going to be 0, 0. Because why? Because the structure of the network that I have somewhere right. I'm going to erase this one and right here. Right. So the structure of network that I have is this. So let me see. It's gonna be like this. Right. So if this node 0, this is node 1, this is node 2, 0, 1, 2. So this 0 now has a parent 0. So as long as we are actually clear about that. All right. So that's good actually. So 0, 0, then you have 4 different possibilities, right? So the node itself has two levels, the parents have 2 levels, 4 different possibilities. Usually using this list. All right. And each element in a list, when you add them up, each list should add up to be 1. Now, why do you have 0, 1, 1? Now this is where the fun starts, the challenging part. You see, on this network, the 1 has 2 parents. One of them is the 0 itself. The other one is the 1 itself. So you have to specify that. They are both of them parents. That's why it says 0, 1, 1. We can handle this. So don't worry about that. So you just specify the distribution here. And then you have a 0, 1, 2. Why do I say 0, 1, 2? Because the node 2 is not connected to the next point in time. So this is not like that. This is like this. The node 2 is not connected. Can you connect it? Of course you can, but we did not. So any structure you like, we did not connect it. Who says that the node 2 should be connected? Like if you consider the structure of HMM, right? So this is one of the structure of the HMM. Perhaps I have to talk about the next video. So I'm gonna say this is input output HMM. So in input output HMM, the observations are not connected. Even in the vanilla HMM, that you have, the states are like this, right? So the observations are not connected. These are the observations. They are not connected. So you don't have to connect them together if you don't want to. And then the parents do. The parent 2 is this. 0 is 0, 1 is 0, 1, and 2 is 0, 1. We saw that. All right. The loopbacks is for the temporal interconnection. For the first time point, we are not connected to time, so we don't have loopback. Loopbacks for a node 0, 0 is 1. For a node 1, 1 also is 1. The loopback is for temporal interconnection. Remember, the node 1 is connected to node 0, but it's not temporally, it's in the static Bayesian network. All right. So ignore this parent 2 again. So repeat it. Both of them are the same. It doesn't create any problem for the code. All right. So now you're going to go ahead and instantiate the object by calling the name of the class. These are the values that we pass through init function. All right. So it's smart enough that the passes a default variable as well. So if you don't pass anything, it would be empty dictionary for the CPD3 parent tree and loopback 2. So don't worry about that. You pass it like this. This is the object that is instantiate. All right. After this, all right. So I made a promise to you that for the most of the problem, we use this function tsBNgen, and then you're gonna go ahead and issue this function, and what you get is the data that you want. All right. You get the data that you want. Now you want to take a look at the data. And this might be the document where the documentation could do a better job, but I make sure I can do a better job here now. So once you apply this one, this tsBNgen will run this Bayesian network because the instantiation part is just initialize that. This will take care of everything, generating sampling data for you. Now here we are gonna go and take a look at the nodes. So BN nodes This method, when you call that, right, it will let you, for example, take a look at the nodes that you have. Why do I have a double list here? What does it mean? The first 0 means which value, the first variable here, this one, it tells you which variable you want to access. 0, 1, 2. Do I want to access the variable 0? The variable 0 is this one. That we have so many colors here to represent the variable 0 is this one. All right, so the variable 0 has how many samples? As many as I specified, 2000, right? I want to look at the sample number 3. And this is variable 1. I want to look at sample number 3. This is variable 2. I want to look at sample number 3. All right, so that's how it works. And if you look at that, it gives you your answer. You can simulate this for as many time points as you like. I actually use this package for some simulation process as well. This allows you actually to compare various algorithms very easily, right, together. Since you have a DAG structure, you have an already explainable model. It's not causal per se, but you can think of it as a very explainable model. It's a Bayesian network, right? Very good. So this is the first example. Another example I want to show you is the last one. I'm going to walk you through that. It's an interesting one. It's a HMM loopback one, right? Hidden Markov model. And I find the hidden Markov model to be very useful. I have a package in Python, MATLAB, R. I am hoping to create a video and release that package as well. And people can handle supervised, unsupervised, discrete, and continuous HMM. It handles anything. It does the cross validation for you. It does the pre-processing, discretization, fitting the mixture of Gaussian. It tells you how many Gaussian you want. It does everything for you. You just click and run, right? So it's in all 3 languages, but I have to have time to release that. But now let's see. So you can use that package along with this to check the effectiveness of your model. Now you have HMM with loopback 1. Let's go through this. So I type a start time. This is import time, and see how long does it take for the code to run. Not an important, very important thing. This is T20. This is N1000. 20 time points, 1000 subject. All right. So look at the math adjacency matrix. We have 2 nodes, right? This is node 0, and let's see how I can show you this like this. This is node 0, and this is node 1. They're better connected together, otherwise they're going to be isolated nodes. Node 1. All right, and then DC. This is discrete. I'm trying to tell you the continuous HMM because states are always discrete HMM. So, and then so this is the initial point in time, and then 0 takes 4 levels. I have 4 states. 0 takes 4 levels. You see in here, and they are all equal likely. The value of the this node, they are all equal likely. At least the initial point, they are all equal likely. And 0, 1 is a Gaussian distribution with how many distribution? 4. Let's start from 0, mu0, all the way to mu3. You can play with this. And now parent is for the first time point. 0 has no parent, and 1 has a parent to be 0, right? So node 0, they're connected. CPD2, what is CPD2? Then this one and this one, right? So this is node 1. This is connected. This is HMM. Right? This is HMM. So 1 is not connected to 1 in vanilla HMM. So you see that we have 0, 0 here, and you have 0, 1. We don't show it like that. We're going to say the 0 node 0, and this is normal. All right. So now you have a 0, 0 for CPDs. Remember, the parent comes first. The parent through the loopback is 0. Parent, the parent of the node 0 is a parent of node 0 for the next time point. And now how many time points you have? 16. 4 times 4, 16. All right. You can go ahead and play with these distributions. So we have 4 lists, and each one has 4 elements in it. And 0, 1 remain the same because through time the node 1 is not connected to anything else. All right. And then loopback is 0, 0 is 1. And the parent 2 for the 0 is 0, and for the parent 1 is 0. Go ahead and instantiate the object. And then you do this. As I made a promise to you, 2 functions, mostly use this one. And then this tell you how long does it take, 2 seconds. And this is, you want to look at the first sample or second sample in Python, actually. 1 is the second sample. So node 0 is the first topological node, the root. And then the second sample, node 1. and then the second sample folder. All right. And how many time points? Remember, how many time points for t equal to 20? All right. So next video, I'm going to walk you through this in a Python and show you how you can run this. The same thing we have done here, but now run it in front of you. Now, so if you like this video, please subscribe to the channel and like and share the video with your friends. Stay tuned. I'm going to release more packages. I have to assign a license to the packages. The HMM would be very useful. And some packages I have for the perhaps feature-based and distance-based clustering of time series and forecasting using LSTM and more traditional network anomaly detection and also missing value imputation. I will try to release them as well. For me, in the meantime, please subscribe to the channel and see you all in the next video. Thank you.